Hi, good afternoon. How y'all doing? Excellent day so far, right? I am so excited to be here with you all. First time in Atlanta, very excited about it. And I'm here to talk to you about recursion, iteration, and JavaScript, and tell you how there's a love story between all three of them. So hello, yes, my name is Anjana Vakil. You can find me on Twitter at my name because I don't have any clever internet handles. And that has links to my GitHub and whatever. I am not an Angular developer, but I write JavaScript, and I love going to conferences and meeting up with just great communities and great events. And the Angular community has been so welcoming to me, so I love being here. And I just let's all give a huge thank you to Zach and to the NG Atlanta crew, Kim, everybody. Thank you so much. What an amazing community. Even non-Angular people can come and have a fun time. So yeah, I am a software developer and educator. I work in San Francisco for a company called Mapbox. If you haven't heard of us, we build tools to help developers like us build really amazing customized experiences for your users that are powered by live location data. So I'm not going to talk too much about our product. I'm happy to chat about Mapbox and learn about if anybody is using it for their things? Not yet? Not yet. OK, maybe one or two people. So we'll all talk later. But I'm not here to talk to you about Mapbox product. I'm here to talk to you about programming paradigms. Because I love nerding out about the abstractions and the mental models that we use when we think about, when we write, when we understand and work with our programs. Perhaps that's because I studied philosophy before I got into computers. So I really love thinking about those abstract levels. So if you want to nerd out about functional programming, object-oriented programming, logic programming, declarative, whatever, just programming paradigms in general, please come find me. Love it. And you also might like a talk of mine on YouTube called Programming Across Paradigms. These slides, by the way, are up on Speaker Deck. My username there is VakilA, so you can find the slides there if you need them later or need the links. So yeah, I want to tell you about two particular paradigms, and you might say that they're star-crossed in a way. And I'm talking about iteration and recursion. Now, it might be a little strange to refer to these as programming paradigms, because usually we think of things like functional programming or declarative programming, object-oriented, imperative programming as paradigms. But I think that iteration and recursion qualify because they are basically two different mental models that we can use to think about how to approach problems as programmers. And in this case, perhaps the sub-problem of programming, which is involving how do we take the same chunk of code and run it multiple times to solve the problem at hand. So iteration and recursion are two alternate paradigms that we can use to think about this problem and approach running code repetitively. So iteration often goes hand in hand with imperative programming, where we're telling the computer, first do this, and then do that, and then do this other thing, follow my commands. And iteration is a way of giving those commands to the computer in loops. So we can take the same chunk of code and run it over and over again in a for loop or a while loop. And at each run of that chunk, at each iteration of the loop, we are going to be changing something. Maybe we're pushing values onto an array, or maybe we're just incrementing a counter of some kind. In any case, we've got values changing over time as we loop. So values changing over time is state. So this is a stateful way of approaching that problem. And now I really like to have something concrete, something visual to remind me of the ideas that I'm trying to think about when I think about these big abstract things. So I love having mnemonic devices. Earlier this morning, Amira had us playing a little game of Guess the Movie. We're going to do Guess the Movie round 2 here. Can anybody guess the movie that reminds me most of the iterative paradigm? A movie where you're kind of trapped in a while loop? Groundhog Day, yes, amazing. So if anybody hasn't seen Groundhog Day, it's a classic, go watch it. Bill Murray is sort of stuck in this infinite while loop where every day he wakes up and it's February 2nd, and he hears the same song on the radio, and so on and so forth. But there's state, right? Because he can remember that he's been there before. He can learn new skills from day to day. So perfect example. So if you want to watch a movie and tell your boss that you're actually studying programming paradigms, this is a good one. You can tell him Anjana said it was OK. So on the other side of the coin, we've got recursion. So if imperative programming and iteration go hand in hand, then recursion is sort of a sub-paradigm or part of the functional programming paradigm, often thought of that way, where in functional programming, we're thinking of our programs not as a series of commands, but as a composition of pure functions, where each function is taking in some inputs and then returning some output. And our program is built up of those. And so in a recursive approach to repeating the same chunk of code, we're not going to be looping. Instead, what we're doing is we're doing that repetition by self-reference. So we've got a function that within its body is calling itself, making reference to itself, and that's how we accomplish that repetition to solve the problem. And in each of those successive calls to the function, we don't really care about the previous calls. All we care about is what is the current input, and what is the output that I need to return based on that. So this is a stateless approach in contrast to iteration. Now, I bet you can guess the movie that I use as a mnemonic device to think about recursion. Inception. Very good, very good. So Inception, if you haven't seen it somehow, is this movie where Leonardo DiCaprio, swoon, is tasked with diving into people's dreams. So he and his buddies, they can fall asleep and go into somebody's dream, and then within that dream, they can go into another dream, and then within that dream, they can go into an even further dream, and basically they can go as far as they want, except that there are grave psychological consequences, apparently. But anyway, at each of those dream dives, a dream within a dream within a dream, they don't really know or are aware of like how deep they are or what's going on in the outside context. Sometimes they don't even know if they're dreaming or not, so they have to have like a little top thing, and I don't know, it's confusing, but anyway. The point is, it's a perfect example of that self-referential recursive approach. So these are two paradigms, I would argue, that are both really valid, useful ways of approaching programming paradigms. And they have trade-offs. They have advantages and disadvantages. Unlike people on the internet, I'm not here to tell you that one is like the winner. Instead, I think that they're both really great for certain problems. We just have to think about how they differ. So when they differ, we often think about the major point of contention between them as being efficiency. So angry people on the internet will tell you like iteration is more efficient. But I think that that's true only if we're thinking about the resources that the computer needs to consume when it executes our code. And that's really just one type of efficiency. I would call it machine efficiency. The time, the space constraints, the constraints on the computer when it runs our code. But there's also another type of efficiency that we should consider when we're thinking about how we create programs, which is the human processing that has to happen when we're reading code, writing it, talking about it, understanding it, maintaining it. And so we could think of that as a different type of efficiency, human efficiency. And so many people find that recursive approach is somehow more intuitive or a better match to their mental model of a problem in certain cases, so maybe more human efficient. Whereas often, iterative code runs more efficiently on the machine. Perhaps that's because the machines kind of think iteratively a little bit. In any case, the idea is that they have these trade-offs. Generally, we want to be thinking about how are both of these efficient, not just in terms of the computer, but in terms of me, the programmer, and my coworkers. So I would say that both of these are equally great solutions for certain problems. You might say that they're two paradigms both alike in dignity. And I write a lot of JavaScript, so it's in fair JavaScript that we lay our scene. Anybody recognizing this? There's chuckles. Yes, these are the opening lines of Shakespeare's Romeo and Juliet. So now, hopefully, I've made my English teachers proud by quoting Shakespeare in a tech talk. And more importantly, I've hopefully made Leonardo DiCaprio proud by citing not one, but two of his movies in a tech talk. So now, I think Romeo and Juliet is a fitting mnemonic for these two paradigms, also because kind of like these the two families here pointing their guns at each other, this is how a Hacker News thread typically reads, where you've got like people yelling like, yeah, iteration, much more efficient. No, recursion is more elegant. Like, there can be only one survivor. Bah. People need to calm down because both of these are great approaches. And so unlike Romeo and Juliet, this doesn't have to have a terrible ending. It can have a happy one. It can be a love story instead of a tragedy. And I think that what is going to bring that happy ending, hopefully this is what we're talking about today, is some love from communities and languages like JavaScript, which are finding new ways to allow us to take elements of one paradigm, bring them into the other, to make both of them better to work with for us as programmers. So this is what we're going to talk about. On the one hand, how can we take iteration, which is theoretically more machine efficient, and make it a bit more intuitive, maybe more human efficient? So Act 1 begins. OK, so we're programmers, so we love trees, right? Everybody's favorite data structure is a tree, of course. No. Anyway, I've got a simple tree here that's made up of nodes that are just represented by this little simple tree node function, where we've got each node can have a value, and then it has to have a value, and then it possibly has a left child, and it possibly has a right child, which are themselves nodes and might be subtrees. And so then I've got a little helper function here, make tree, which is going to take in a node type, like my simple tree node, and spit out a tree with the integers 0 through 6, just for the sake of demonstration. So this is the tree that we've made. It's a simple tree. OK, now, if I was going to ask you, how do I traverse a tree like this? How do I get out all of the values of this tree, ideally in the order that I want them? How would you describe that to me? Think about it for a minute. OK, now I don't know about you, but I might say to my coworker or whoever, OK, well, start at the root. Start at the root of the tree. Tell me what that is, what the value of that is. And then if there is a subtree on the left, go through that, traverse that, and tell me all of the values in it. And then if there's a subtree on the right, go through that and traverse all the values. So if you described it like that, you would be using a recursive approach to do that traversal. So here I've got that kind of coded up in a very simple little function here, recursive traverse or recurtrav. And what I'm doing is just logging the value of a root node of a tree, which represents the whole tree here. And then if there is a child on the left, I'm going to recursively call the same function to traverse all the nodes there. And then if there's a child on the right, I'm going to recursively traverse all the nodes there. And if there's no children, I'm done. So this, if I run it, it gives me the values. It works, yay. And hopefully, I don't know if you all agree, but this is pretty intuitive from my point of view. So it's pretty easy to read and write, pretty human efficient, I would say. So what if I asked you to write a function to traverse the tree, but not using recursion, only using iteration? Give me a moment to think about it. OK, so this one took me longer to think about. I don't know about you. And here's one way that you could do it. Give you a second to read it. OK, quick show of hands. Is this harder to understand than the previous example? Yeah, I think so. Most people have raised their hand. Well, I don't know about most, but at least half. The other people are perhaps thinking about it. So here, this is one way we could iteratively traverse a tree. I can run it. It works. But I don't know about you. I don't find this so intuitive. It's like, what is going on here? All right, we've got some kind of to-do list of like the nodes that we have to traverse still, and then we're looping over that. And we're taking off the first thing on it, and then logging the value. And then if there's a child on the left, we're putting that on the one end of the array. And if there's something on the right, we're putting that on the other end of the array. And then we keep going until we run out of stuff to do. Like, it works, but I don't know. That doesn't mesh as well with my mental model of how I want to go through this tree, personally. So what if we could figure out a way to iterate over the tree, looping over the tree, that is more intuitive, that's more how you would say to somebody, hey, just go through each thing in the tree and tell me what it is. So wouldn't it be cool if we could just put this tree in a for loop? Well, thanks to JavaScript, we can. So in 2015, in ES6, we got some cool iteration protocols. Well, I think they're cool, that allow us to define custom iterables by using the symbol iterator property and iterators that are built as generators using function star, which we're going to look at in a moment. And so once we've implemented a custom iterable like this, we can just take our whatever object, in this case a tree, and put it in a for loop. So how would that work? So here I'm going to make a new type of node called an iterable tree node. And this, so far, is going to look pretty much like my recursive version, my simple tree node version. And what I am going to claim is that we can take our recursive approach to traversal and bring it to our iterable tree by using these iterator protocols. So what I'm going to do is create a new iterator that I'm going to assign to the symbol.iterator property of the tree node. And that iterator I'm going to implement, and I'm going to name it very cleverly recursive iterator, because again, good at naming things. I'm going to implement that as a generator, so I've got my function star. And the structure of this is going to be almost identical to the recursive traversal function that I had written before. It's just instead of logging the value, we're yielding it. And then instead of making a recursive call to the function to traverse the child trees, the left and right children, what we're going to do is use yield star to basically iterate over those left and right trees using the same iterator and successively yield each of those values out. So hopefully, this little recursive iterator here is just as easy to think about as our recursive traversal function before, and a little bit more human efficient here. And now, I can make a new tree, a better tree, with my little make tree helper that's going to take in the iterable tree nodes now, and I can take that tree and just stick it in a for loop and log out each of the values. I don't know about you, but that makes my heart just like feel a little warm and fuzzy inside. This is so much nicer to me than doing that weird to-do list thing. So what have we got here? Well, we've got even better news coming up in ES 2019. All of these iteration protocols go async, so woo. But most importantly, we've got a way for JavaScript to bring a little love between the iterable for loops that we know and love and the recursive mental model that we find a little bit easier to traverse trees to give us some more human-efficient iteration. So that was Act 1. Now, how about Act 2? What about recursion? So recursion, let's say it's perhaps a bit more human-efficient. How can we make it more machine-efficient, more performant? Act 2. OK, so here's a little recursive function called recursive inception, because I love talking and thinking about Leonardo DiCaprio movies, that I've just wrapped in a little script. So see if you can see what it does, like intuitively. What this is going to do is if I give it an integer that represents kind of like a depth of dream diving, it's going to spit out a string that describes like how many dream layers Leo is in. So if I give it 3, it's going to say, oh yeah, he's in a dream within a dream within a dream within a dream. And if I give it 30, it's going to give me 30 within, so I'm not going to say that because it'll take the rest of my time. And by the way, this is because human language also has recursion, so we can keep nesting these clauses, nesting these phrases, the within a dream, within a dream, within a dream, within a dream, as long as we want. Linguistically, that's totally allowed, because language is super cool. Also love nerding out about that, so if you want to do that, come find me later. Anyway, what happens if I give it a bigger number, like 3,000? Well, it takes it a minute, but I do get a bunch of withins here. They don't fit on a slide. You can take my word for it. And I said that language should allow us to do this infinitely, so what happens if I give it a really, really big number, like 30,000? Stack Overflow. Maximum call stack size exceeded. I can't do it. This sad little message comes up in my node process. If you run it in Firefox, you'll get like too much recursion. Like, you're cut off. You don't have to go home, but you can't recurse here. Like, not happening. So anyway, so I get this sad, like heartbreaking Stack Overflow message, and that really bums me out because I wanted to see how far Leo could go before his brain explodes, which apparently is 30,000. I don't know. So what's going on here? Well, turns out that recursion and call stacks are not friends. So when I'm running this code, my little recursive inception module, let's say I run it with just that's basic input of 3. I've got some finite amount of memory allocated for the stack that runs this process. And there's some other stuff on this that has nothing to do with my code, globals, et cetera. But when it comes to the program that I'm trying to run, I have some finite amount of memory. And when I make this recursive inception program run, what it's going to do is, first of all, make a call to the recursive inception function with an input of 3. That's going to mean I need a frame to be put on the stack to represent that function call. This is not what JavaScript sees when it sees this frame. This is what I, as a human, like to think of the frame as being, because it helps me understand better what that represents in terms of the code I wrote. So just disclaimer, this is not how JavaScript talks about stack frames. But in any case, what I've got is basically a representation of that call to recursive inception with input 3, which is going to do whatever I told it to do. In this case, that's going to make a call to recursive inception with input 2. And so that's going to need a new stack frame for recursive inception with input 2. And that's going to make a call to the same function with input 1. And that's going to make a call to recursive inception with input 0. Now, once I get hit 0, I've hit my base case in my recursive function. And so now I'm no longer going to make a recursive call to the same function. I'm just going to output whatever my smallest possible string is, which in this case is just a dream. So phew, I don't have to make another call because I am just butting up against the limits of my memory here. Now, in real life, you get like something more than 4 different frames that can fit on the stack, but the principle applies. So now this recursive inception 0 returns to the calling context. So that's the frame below it, which was my recursive inception 1 call. So that's going to get the output a dream. It's going to do whatever it has to do. In this case, it's going to concatenate on another phrase within a dream. And that's going to return back to the previous frame, which is going to add on even more, which is going to return back to the previous frame, and so on and so forth until I get my output, a dream within a dream within a dream within a dream. It's hard to keep track of. Anyway, so now what happens when I run it with input of 30,000? Well, you can probably see where this is going. Same deal. I still have a finite amount of memory that I'm working with. It's going to start off with that recursive inception call with input 30,000, and then that's going to need another frame for one for 29,999, and that's going to need one for 29,998, and so on and so forth, until ultimately I'm going to run up against a case where I no longer have room to put the next stack frame on the stack, and so that's blown my stack now, and sad face, call stack size exceeded, too much recursion, go home, Anjana, etc. So this is no fun, because recursion, we should theoretically be able to do this infinitely, but machines cannot do things infinitely. They have finite resources. So wouldn't it be nice if we could find a way to do this recursion where we didn't need to keep adding a stack frame for every recursive call? We didn't need to have like a linear number of stack frames, but instead, what if we could figure out a way to do it without adding more frames to the stack with a constant number of stack frames, basically? And this is possible if we have a really cool feature of some JavaScript engines called tail call optimization. So tail call optimization is an implementation feature that an engine, a compiler, a processor, like a JavaScript engine, for example, could implement that allows us to recycle or reuse stack frames or resources on the stack if we don't need to remember anything about the previous frame, about the previous context that was trying to call the next function. And that requires us to write our recursive functions in a special way where the recursive call is in what's called tail position, which we're going to look at in a moment. And you might have heard the term proper tail call, so this is what this is referring to. So what does this mean? What is tail position? What is a tail call? What is tail recursion? So what I was thinking anyway. So our previous function, our recursive inception function, is not tail recursive. And that's because the function has to do more work after that recursive call returns. So here you can see that we're making this call to recursive inception of n minus 1. Whenever that result comes back, though, we still need to do something else. In this case, we need to concatenate another string onto it. And this means that that call, recursive inception, is not in tail position, because it's not the absolute last thing that the function does. So what would it look like if we wrote a tail recursive version of this inception function? So let's do it together. For a tail recursive version, one handy trick that we can use is to actually not do the recursion in this main tail recursive inception function, but create a little helper function that is going to be the recursive function that does this. I'm going to call it incept because I'm, again, just really great at coming up with clever names. And this little helper function is just, I'm going to directly call it from my outer tail recursive inception function with whatever input it was given. So that's going to kick off the recursive process. Now, in my previous not tail recursive version, I didn't have to keep track of like how many dreams we had already gone down, because basically the layering of the stack frames was doing that for me. I'd say, oh, I need to add another within a dream, I need to add another within a dream, another, and so that's what allowed me to achieve that depth. In a tail recursive function, we can't add on that extra within a dream, because that would be more work after the recursive call. So we have to find some other way to remember the history of like how far have we come already? How deep is Leo in? And one thing that we could do is use or the common way of doing this is to use an accumulator variable. In this case, I've named it dreams, that is going to sort of amass that history and remember it for us so that we no longer need the position of the stack or the layering of the stack frames to do that. So in this case, my dreams accumulator is going to get passed into this incept function, and then in my base case where we're not actually doing any recursion, we're just going to return whatever the value is of that accumulator. And then in the recursive case, before I make that call, I'm going to add on that within a dream to the accumulator so that the next call to the function is going to have that in its memory, is a way of thinking about it. So when I kick off this recursive process, I'm going to use whatever my original kind of base case, or like the smallest possible string was, as my initial accumulator. So these two functions now are equivalent, and now this call, this recursive call, is the absolute last thing that this function does before it returns. It's just going to return that value right back. So this is now in tail position, meaning it's the absolute last thing the function does, is make that call. OK, so now I'm going to try and run through this because I think we're at time. But the problem that we had before, running into that Stack Overflow, is going to look a little different now if I run this code, this tail recursive function, on a JavaScript engine that has tail call optimization. This is what's going to happen. So we're still, as before, we have a stack frame for the function called tail recursive inception. That's going to call incept with inputs 3 and a dream, the initial accumulator. That's going to need a new stack frame for that. And that, in turn, is going to make another recursive call to incept with input 2 and a little bit longer accumulator. And that's going to need a new stack frame, just as before. But here's the thing. When this call to incept of 2 returns, the call to incept of 3 doesn't need to do anything else. So I don't actually even need to remember that I made that call. I can just throw out that frame. Or better yet, since we're eco-conscious, recycle it. And basically just get rid of it. Just throw it out. And now this incept of 2 is now the top, or the only thing on my stack besides the initial tail recursive inception call. So what I've done is elided the stack. I've taken out something in the middle. It's now shorter. Now we're going to need a new frame for the next recursive call to incept of 1. But same as before, now I no longer need the incept of 2 frame. Recycle, gone. Now I'm going to need a recursive call to incept with input 0. That's going to get a new frame, but now I don't care about incept of 1 anymore. Gone. And now, finally, I don't need to do any more recursion. I can just return my accumulated dream string and ultimately get back my output. So what we've just done is we've run this recursive function, but with a constant number of stack frames, because every time I add one, I'm also taking one away. So now, what we've got is sort of as if we had written the solution to this problem recursively, but JavaScript kind of iterates it more like a for loop. It's almost like, this is not exactly what JavaScript sees, but it's almost like we say, OK, you're going to need an n and a dreams. N's going to start out at whatever, 3. Dreams is going to start out at a dream. And you're just going to keep looping as n goes to 0. You're going to keep adding dream states, and you're going to keep decrementing n. So it's almost like JavaScript can execute my recursive code iteratively. So, all right, now we've got our tail recursive inception function. I've wrapped it in a little script like I did before. And now we're going to run it with a really high input number, 30,000. And ready? Go! Crap, we got another call stack size exceeded, stack overflow, too much recursion error. Anjana, you lied to us, you betrayed us, you broke our trust. WTF. So remember how before I said some JavaScript engines implement this with an asterisk? Yeah, that's a pretty big asterisk. Not that many do, only a couple, basically. WebKit, Safari, has this feature, tail call optimization. But, and V8, so Chrome and Node, had it, but got rid of it. Because it turns out that messing with the stack is not a wholly, there are disadvantages. So, for example, you might run into problems debugging if you have kind of messed with your stack trace because you've messed with what happened, and so you can't see the actual calls as they were made. Not ideal. There's a great post by the V8 team about how they implemented, or why they decided to take this feature out, and it's hotly debated. There's a lot of discussion. It's ongoing. For example, there's also a proposal out to get this into WebAssembly. Again, under discussion. It's a contentious feature. But suffice it to say, some JavaScript engines have it. For example, Node 6, which I can switch over to with MVM. And I do need to use a flag to expose this particular feature, Harmony tail calls, or just Harmony. But if I do all of these things, all these asterisks, and I run this in Node 6 with Harmony tail calls enabled with 30,000, I get a whole bunch of dreams. It takes it a long time. But you can try it out if you don't believe me. This actually does happen. This works. So yay! Wonderful. Now we've got more machine-efficient recursion thanks to a little love from certain JavaScript engines and the way of executing this code in a more iterative fashion. So, OK, I'm over time, wrapping things up very quickly. Iteration, recursion, two great paradigms, if you ask me, that are now made even better with elements of each other by JavaScript. So what this does is now give us as programmers more tools, more better options to solve the problems that we need to solve so that we can choose the best fitting solution. If you ask me, that's what we should all be doing as a community, is trying to find ways to give ourselves more tools so we can find better solutions, better fitting solutions for the problems we have. So yeah, there's some links in my slides, which again are up on SpeakerDeck. I can tweet it out later. Shout out to some awesome communities I love, Recursion Center and MozTech Speakers and Outreachy. If you haven't heard of any of these, come ask me about them afterwards. And big, big thank you to NG Atlanta for having me, and to you all for listening. Thank you so much.
So I felt like we were in a bit of a drama movie going on this whole time. I was a little worried that we were going to have a poor ending, but it ended up being a happy ending, so we actually were able to go.
Yeah, and it's funny that we give Safari a lot of shade, but they were the first browser to implement tail call recursion. Yeah. And other browsers didn't. So like, props to Safari for once.
We hated on it earlier. Yeah.
Lots of props to Safari. It's hard to make a browser.
Yeah, we'd like to pick on it a little bit. Like service workers took a while, so just a little bit of picking on them. You got to poke.
That was a, I got to say, like, no offense to everybody else, that was one of my favorite talks because you took a really, really complex topic, like tail call recursion, which I've never seen a talk about because it's so complex to explain to people. It took me hours to understand it, and you explained it in 25 minutes. That was
examples
fantastic.
tied
Maybe
it together so
Sorry,
nicely. It was so easy to understand. It was good.
Well, thank you so much. I'm so glad it was useful. I hope it was useful. I found that this kind of thing, to me, I'm really lucky because I've been part of some really great communities where I've had people totally willing to sit down and talk to me in ways that I could understand about complex technical concepts like this. And so really when I give talks like this, I feel like I'm just channeling all of the great teachers and mentors and peers that I've had the joy of learning from over the years. So yeah, I think I had the good fortune of spending some time at a place called the Recursion Center that I just mentioned briefly at the end here, which happens to have the word recurse in it, but isn't only about recursion. It's a community of programmers, people who want to get better at programming, where I think was the first place that somebody sat down and told me, hey, have you heard of this thing, tail call optimization? And I just, oh my God, that's so cool that you can do that you can mess with it. And there's some really great resources and talks from that community that I'll try and dig up and tweet out and share with everybody.
That's exciting. So everyone has to follow you on Twitter now because they're going to get a lot of great resources. And I love that you like the Vespa.
Oh, man.
So, but I have a question for this. Living in San Francisco, which both Jem and I do, I live on a fairly steep hill. How are the hills? How are the hills with the Vespa?
Painless.
Really?
So great. Yes. And you should see cars trying to do that.
Yeah, no,
and I'm
like,
just like
I have all-wheel drive, and there's days where I'm like, am I going to make this? Yeah.
Yeah, so. No, I mean, you got to be careful when turning on a hill. I live on Telegraph Hill. It's a really steep one, and you definitely need to be careful when turning. But going up and down, no problem. It's got a little rev to it. It's great. Now those electric scooters. I don't know if they have something like that in Atlanta, but they're basically these little electric mini Vespas.
Yeah. Yeah.
And they, on the other hand, do not have a fun time on the hills. I once had to kind of slalom up to like make it happen. So yeah, be careful.
I'm not a fan of those. Like people on their, I won't go into my rants about people on scooters, but they're kind of jerks. They like cut through people, but they're not that fast.
Because
So
they're just renting them for the moment. They're
That's
not
true.
like, they haven't learned to use them all the time.
I once saw someone on a scooter on 280, one of the freeways, and they were just doing like 40, and I'm like, what are you doing on a scooter? It's just dangerous for everybody. I was scared for them.
Yeah, no, I don't take my scooter on the freeway. I don't need to. I mostly use it around town. But I would say for San Francisco, it's, for my money, the best way to get around because you can't really rely on Muni in San Francisco. And all the scoots and things like that, they're all gone from downtown by 5 p.m. And cars, parking, driving, traffic, bananas. So scooters are the
Right
way
on.
to go. Scooters 2019.
Tail call recursion.
Yeah,
On the scooter.
exactly.
Well, thank you so much. The talk was amazing. We
Thank
appreciate
you.
sharing
Thank
that
you.
with us. So thank you so much. Round of applause,
Thank
everyone.
you. Thanks so much.